Hello and welcome back, and thank you very much for watching this lecture video. I'm gonna start the lecture with benzylic oxidation. If there is a carbon straight attached to benzene, technically to the ring or to the phenyl ring, and that carbon, it has a hydrogen atom. Whenever it gets exposed to chromic acid or potassium permanganate, the methyl group or any alkyl group with a hydrogen, it will be oxidized and it will turn to carboxylic functional group. So in this case, because both methyl, they have 3 hydrogens, and in that case, I'm going to say each methyl, it will be oxidized and it will turn to CO, and then O attached to hydrogen. Okay, so we got the carboxylic group, and we will have the same story on the left side. We'll have a carboxylic group. So as you see, both methyl group got oxidized. Now, the second molecule, we have 3 hydrogens on this carbon. So that one, it will be oxidized, and it will turn to C double OH, which is equal to this group. Is a carboxylic group, but the top one, because we have a tertiary carbon, and in this case, actually, well, it will be quaternary because attached to the ring, and so this one is attached to the ring and then on like technically attached to 4 carbon, and it will not get oxidized and just simply stay as it is. So nothing is going to happen to that carbon. The one I'm going to highlight this carbon, stay as it is. Now, I want to list some of common reactions for benzene molecule. As you see, we can take the hydrogen and benzene molecule, replace it by halide. In that case, we say we are dealing with halogenation. If you replace it with NO2, nitration, SO3H, it will be sulfation. If you replace H by OH, or technically oxidize it, and in that case, we say we are dealing with hydroxylation. If you can replace H by alkyl group, and it will be alkylation. And if you want to replace it by an carbonyl group, and in that case, we say we are dealing with acylation. I'm gonna try to practice some of them, but first we need to review the electrophilic and aromatic substitution. The benzyl ring is not gonna go through electrophilic substitution easily, and the reason for it, because it's stable. There is the aromaticity here, and benzene does not want to lose it unless you have a cation or a species that is super unstable and is looking for electron. So whatever you create as an electron file, that one must be thirsty of electron, and in that case, the phenyl ring will share electron with it. And so first step is going to be a really slow step, and because we are technically getting rid of the aromaticity. And in order to restore it, we need to have a base, and that base must be strong enough to take this hydrogen as H plus from the system. So it's going to take it out as H plus, and it will leave those 2 electrons. It will give them to carbon, and that carbon is very soon is going to share them with a carbon that it has a positive charge, and it will restore the benzyl ring. Okay. Now, the first step, as I said, the first step is the rate determining step. So the addition of the electron file technically to the ring, and that's going to be the rate determining step. And if you look at it from the phenyl, from the benzene is sharing 2 electrons with the electron file. So benzene is the nucleophile because it's sharing 2 electrons with the electron file. And that's the reason, like we say electrophilic aromatic substitution, and the nucleophile here is the ring or the benzene, but the species that we are actually adding to the phenyl ring or to the benzene is it has only empty orbital, and it's not going to share electron technically with the ring. It will take electron from the ring. The second step, it will be fast step, is just technically hydrogen abstraction from the system, and it will restore the benzene ring. Okay, let's start with halogenation. Halogenation, it will initiated by Lewis acid like FeBr3, and it will react with bromine, and then simply it will replace one hydrogen atom. So say we have here, we have a hydrogen atom. Hydrogen atom, it will be replaced by IBr. And what else we get? Another product that we get, it will be HBr, that acid, and also we will restore the FeBr3. We get that one as well. Okay. And okay, next, so the first step is going to be this. We have Br. It will react with FeBr3, and this one technically it will be added. Okay, one of the bromine will be added to the iron, and if that case, if that one happen, if we add it to iron, and very soon we're gonna have a positive charge. So this one, it will have a positive charge because this one was added to iron. So what do we get? We get FeBr4. This one, it will be -1 plus Br plus. So this species, it has a positive charge. Now this one, and it will be sensed by the ring, and the ring, it will try to go after it. So now our nucleophile will attack it, and we get this species. So this one, you can call it a brominium, and is a bromine with a positive charge. That means we're going to have a positive charge on this carbon. Okay, we need to restore the aromaticity. And how do we restore it? We need to have a base, and our base, it will be FeBr 4 times with a negative charge. This one is going to go after hydrogen. It will go after this hydrogen, and it will take hydrogen as H plus, and those 2 electrons that will be given to carbon. And now we get double bond there, and bromine is here. So the H, it will be paired with the bromide, and it will turn as HBr plus, we will get FeBr3 back. So the main product here is going to be replacing hydrogen by a bromine atom. Okay, if you repeat this technically experiment, but this time you're using nitric acid and sulfuric acid. And when you mix nitric acid and sulfuric acid, you will get a species that's is an electrophile and electrophilic technically species, and is an NO2 with a +1 charge. And as you see here, oxygen, any of those oxygen has 0 as a formal charge, but nitrogen, it has a +1 charge. Nitrogen is the electronegative element, so it's not going to be happy. And so the ring very soon is going to detect technically the nitrogen, and it will find nitrogen that is short of electron, and it will attack it. And if that one happen, we will get nitrogen. Okay, nitrogen attached to the ring, and now we will have nitrogen attached to one of the nitrogen through a double bond. To one of the oxygen. This oxygen, it has 0 formal charge, but the second oxygen, it will take these 2 electrons, and now it will turn to -1 because it's the most electronegative element here. Now, what's the charge on nitrogen? Nitrogen still is going to be a +1. Okay, +1, it will be canceled by -1. That one will be 0. So we need to have a positive charge somewhere, and that positive charge, it will be here. Okay, now we got a positive charge inside the ring. We need to have a base to take hydrogen. This hydrogen is going to be really acidic hydrogen. So if we introduce a base there, something like water, that can do the job for us. It will go after hydrogen, it will remove hydrogen, and it will give us this technically compound. In plus, we get hydronium ion. So the main product is technically replacing hydrogen atom by NO2. And this reaction, we call it nitration. Okay, the hydrogen atom on a benzyl molecule, and benzene molecule got replaced by NO2. And correct name for the reaction is nitration.